It's okay? Okay. Okay. So good morning, everyone. Today we have a long day, you see. So this is a post-champagne section. But so I don't know if we will have time to cover everything. But so maybe we will split this between the morning and the afternoon session. But before starting with the today we are going to see some few examples of what Filomena explained yesterday in a more general way. She gave yesterday some of the theoretical tools that are used in nuclear reactions, but many of these tools are cannot be directly used for practical calculations. We need to make approximations to these exact expressions. They are useful to derive important results, but in practice we have always to make some kind of approximations. Okay, so today we will see one of the most popular approximations that is called the coupled channels method, and a simplified version of this that is called the DWBA method. This method can be applied to both inelastic scattering and also to transfer or to dark channels, but today we will focus on inelastic scattering, and also Monday inelastic scattering plus breakup, that is a kind of inelastic scattering, and Filomena next week will give more on coupled channels or DWBA for transfer reaction. So the first part is just a general overview, so don't get scared about so many. These are things that you know for sure, but just as a warm up and to make sure that we all set in more or less in the same language, in the same situation. It's good that we review some concepts. Some of them were already given by Jeff the first week, but anyway, I remind you some of these concepts. So we are now trying to study a specific kind of reaction that is inelastic scattering. So inelastic scattering is an example of a direct reaction. So you know that we have direct and compound reactions, and this division is done according to the typical time scale in which this process takes place. So a direct reaction comprises elastic, inelastic, transfer. These are the fast processes in which typically only a few degree of freedoms are entering into the reaction. So they are characterized by typically a small momentum transfer. So they are, and these reactions are typically forward peaked, not always, but many times forward peaked. In compound nucleus reactions, you know that the nuclei collide and they tend to form some compound system, so it loses its identity. This compound will live for some time and then will decay, producing some fragments. But we will be studying the first part of reaction. So first of all, we will study inelastic scattering to bound states, and then we will extend our methods to the continuum. So so far we have been discussing about elastic scattering, but we know that nuclei are not frozen objects. They have some degrees of freedom, so when they collide there is a probability for them to get excited, for either the projectile, the target, or both of them. This is one of the things that might happen. So this is an example of such a situation. So we have a beryllium-11, described here as a beryllium-10 plus a neutron. It collides with a lead target, and one of the possible processes that may happen here is the excitation of the beryllium-11, maybe to this one excited state that is very close to the ground state. So this is an example of excitation. But as I said, first we are concentrated in the situation of inelastic to bound states. We know that in general our nucleus will have a spectrum with the bound states and unbound states. So but we are today concentrated only in these kind of processes. So inelastic scatter is an example, as I said, of a direct reaction in which the nuclei make let's say a glancing contact. I don't know if this is the correct word, and then separate. So they just touch gently each other, and they don't lose their identity. So they exchange some momentum, and one of them eventually gets excited, and this typically occurs because the reaction is peripheral. For a head-on collision, typically other processes like fusion, compound nucleus will take place. So this happens because we have a peripheral reaction in which they barely touch each other. Okay. So in order to model these reactions, since it's very difficult to tackle the problem from first principles, so we have to rely on some simple models. So there are two categories of models: the collective model and single particle models, and in between we can imagine some other kind of models, but these are like extreme situations. So in a collective picture of the process, we can imagine that one of the nuclei will experience a sort of coherent excitation that involves the motion of many nucleons at the same time. And so this can be many times interpreted in a macroscopic picture as vibrations of the surface of the nucleus or some rotation of the nucleus, and there are other possible modes or other possible collective modes. But these two are the most famous, and these are actually we will only consider rotations after. Another extreme situation, like here in beryllium 11, is the single particle picture. So in the single particle picture, we imagine that the excitation occurs because one particle or one cluster gets excited. So we tend to emphasize here, we have 11 bodies in beryllium 11, so we tend to emphasize one particular degree of freedom, that is the degree of freedom corresponding to the motion of this additional particle, the halo. This is a halo system, so this weakly bound neutron relative to the rest of the nucleons. So this is just a model. We are simplifying our 11 body problem to a 2-body problem. Okay. So in both cases, these are, as I said, some extreme models to describe in a simple way what is happening. In practice, we have to keep always to bear in mind that what is happening is what we have are excitations between the physical states of the system. So the different models are just different ways of interpreting the nature of these levels. But physically, what we are describing are excitation between these levels that can be more complicated or less complicated, can be some collective or some single particle, but in practice, this is what we are trying to describe: transitions between these discrete or continuum levels. Okay, this is our goal here, to develop a model or some models that allow us to get some information on the structure of these nuclei by measuring inelastic scattering, and to make the connection between what we measure in the reaction and the structure of these systems. This is our goal. So just also as a reminder, the Q value for an inelastic process is very simple. So imagine you have a projectile excitation. So A goes to an excited state, A star. So this is the energy balance, including the masses of the nuclei. And this A star includes the excitation energy of this final A. So if we introduce what is called the Q value, you remember that Q value is just the difference between the initial masses and the final masses of the products. So we get that in this particular case, and using this, the Q value is just minus the excitation energy of the nucleus being excited. Of course, if both of them are excited, then we have to sum here also the excitation energy of the other system. So an inelastic process is always characterized by a negative Q value. And if we use this definition in this expression, original expression, so we get that the center of mass kinetic energy, the kinetic energy is in the center of mass in the final situation, is the initial kinetic energy plus the Q value. And these Q values, remember, is related to the excitation energy. So by measuring the kinetic energy of the products, we get immediately information about the excitation energies of the excited states that are populated. Okay, so for example here, if the kinetic energy in the final situation in center of mass is the same as the initial one, this means that we are measuring elastic scattering. So let's see a specific example. So imagine we have an experiment in which a proton scatters by a lithium-7 target, and the target gets eventually excited to one of the possible excited states. Okay? So in this experiment, what one could measure, so the natural measure observable here is to measure the angular distribution of the protons, right, and the energies of these protons. This is what one naturally would measure. Even a theorist knows this. So this is a real spectrum of this experiment. Of course, we do the experiment in laboratory, so this is so we have to convert eventually from laboratory to center of mass. So there are some kinematical expressions that take place, but we will not enter into these complications. So as I said before, from the proton energy, we can directly obtain information about the excitation energy. So this is a spectrum of some arbitrary units, a number of counts, for example, as a function of the excitation energy of the, in this case, the lithium-7, because the proton cannot be excited at our energies. So we immediately recognize some peaks and some structure here, some events without a defined structure. So the first thing is what information can we obtain from this before doing any calculation? So if we compare this with a spectrum, with a known spectrum of lithium-7, we immediately recognize that, well, if we know that zero excitation energy should correspond to the ground state of the system. So this is just, this peak corresponds to the elastic scattering at this angle. It was 25 degrees, okay? Then there is an excited state, but it is very close to the ground state. So in this particular experiment, it's not resolved from the ground state. It's not separated. It's a very common situation in experiments when you have closed levels. Sometimes it's difficult to disentangle. So maybe you have to rely on some theoretical calculation to estimate how much of this peak corresponds to elastic and how much to inelastic. So this is where the interaction between the experimentalist and the theorist makes sense for one of the many situations. Okay. Sorry. And then we have this peak that's according to our level spectrum corresponds to this 7½ minus. This is actually a resonance because the continuum in lithium-7 starts somewhere here, actually in this line. So everything that is above this line corresponds to continuum levels. So we see that in these continuum levels, there are some lines that some of you will recognize immediately as, what are these? Resonances, okay? But then we see some region without any particular structure. So, well, this is everything we can say so far from this. So we just, by observing the spectrum, what we can get before doing any calculation is that the proton energy spectrum, as we expected, shows some peaks, and this is a signature that we are measuring the scattering on something that has some degrees of freedom and it's getting excited, so we have peaks that give us information about the excitation energy and the spectrum of the system. Then the height of the peak, that is related, we know, to the cross-section, after scaling this properly with the beam intensity and so on, the density of the target, blah, blah, blah. then this is related to the cross section, and this peak is different for each state. Just by looking at the spectrum, we don't know the reason for that, so then we have to develop a theory that tells us how big this peak is and what information we can get from this. And then not all the peaks have the same width. Some of them are very narrow, some of them will be broad. So again, this is something that we cannot get directly from the spectrum. We have to rely on some theory. And then, as we saw above a certain excitation energy, the spectrum, we still get some counts here, but without any particular structure. So these are just sort of fluctuations, that we get something. So the system can excite to this region, even if there are not particular levels there. So this will be actually the subject of Monday, but just to keep this in mind for Monday. Okay? So these are the things that we can learn from the spectrum and the things that we would like to learn. So as I say, we will concentrate today only in the bound region that for lithium-7 contains only two states, the ground state and this fair excited state. Above this energy, 2 point something, the lithium-7 breaks into an alpha particle at a triton. So above this excitation energy, the system will break into these two clusters, and we don't have lithium-7 anymore. We might have some resonance that looks like a bound state in some sense, but we will have also some continuum that doesn't look like a lithium-7 at all. Okay? So let's go to the fun. So Kapell-Channels method. So to answer some of the questions that we have been posing in the previous transparency, we have to rely on some model. So we can start from the general expressions that Filomena was developing yesterday, but now we want to go from the world of the ideas of Plato to the real world, because we want to do a calculation and to get a number to the beautiful world of ideas. I'm not saying that. So it's a very beautiful, but then at the end we want to get a number, and from this number to get some information. So we necessarily have to make some approximations to these beautiful expressions, to these beautiful theories. So this Kapell-Channels scheme is a way of doing this kind of approximations. So the idea is that in our model, so starting with a two-body model without any degrees of freedom, our Hamiltonian was very simple because it contained only the kinetic energy of the relative motion between the two bodies. But now we want to describe explicitly the degrees of freedom maybe of the target, because we are thinking on this proton lithium-7. Lithium-7 was our target in our example. So we have the kinetic energy. We have to add some Hamiltonian with this psi. This is psi. Psi? What? There are 4 or 5 Greek letters that I call psi. So, okay, this will be psi or psi or whatever. And so this Hamiltonian, depending on these degrees of freedom that we have not specified, because we don't have specified our model, will describe just the lithium-7 in some model. Can be a seven-body problem, some ab initio, very complicated model that nowadays can be done, but probably it will not be very useful to get some simple information. So we don't start from such a complicated model. We want to do something simpler than that. And in the interaction between this projectile, this proton and target, this will depend, of course, on the relative coordinate, the relative vector, capital R, between them. But if we want to describe explicitly the possibility of exciting this lithium-7, then this interaction must depend also on the coordinates of the target. So these big psi coordinates appear also here. Okay? So this is the general form of the Hamiltonian that we will use for as a starting point in any Kapell-Channels calculation. So this is a definition of what I have said. This Hamiltonian, this model Hamiltonian, since we don't want to be too ambitious and to describe the full spectrum of lithium-7, we will be happy just to have a model that describes maybe the ground state, the first excited state, maybe some of the resonances. That is what we are measuring in this experiment. We are not measuring lithium-7 at 20 MeV of excitation energy. We are just measuring a few MeV, and just we want a model that describes this low energy spectrum. So we will be happy if we have a simple model of lithium-7 that gives some prediction, some model for these excited levels. Okay, so this Hamiltonian will contain some eigenstates. This is just to set our notation with some epsilon n that are the internal energies. So I will call this epsilon the internal energy, excitation energy, so binding energy. So it will be negative for the bound states and positive then for the resonances and continuum, so on. And then the projectile target interaction will be in general the sum of the interactions. This P stands for the projectile, or the proton in our case, with each of the constituents of the target of the lithium-7. So this sum, this n, could be a 7 if we have a 7-body model of lithium-7, but if we use a 2-body model of lithium-7, alpha triton, then this sum will contain only 2 terms. So the interaction of the proton with the alpha particle, proton triton. So it will obviously depend on the model that we are using. Okay? Any questions? You have to make questions from time to time, so I have time to drink some water. Okay, so now next step. So the idea of the coupled channel, so far there is nothing related to coupled channel, just we said the Hamiltonian. So the idea of the coupled channel is to expand, to make an expansion of the total wave function of the system that will depend on both the relative coordinates and also the internal coordinates in a set of states of the target in our case. So you see that this is the ground state and then some excited state. So this defines in the language that introduced Filomena the previous days, this is the P space. So this is the part of the space, or the model space, that we want to describe explicitly. So if this sum is restricted just to the ground state, our P space will correspond only to elastic scattering. So this will be our model wave function. That is what we have been doing in previous days. But if we want to go beyond elastic scattering, we want to describe inelastic scattering maybe to the first excited state, this sum may contain, for example, here the excited state of lithium-7. And of course, we could be more ambitious and try to include some resonances, but for that we have to first to know how to include in this sum the contribution from states that are in the continuum. The first day, Jeff gave us some indications on how to do that, and on Monday we will revisit this problem. But today, this sum will contain only discrete states, so we don't have to worry about this kind of problems. Okay? So, what is the meaning of these chi's here? So we have, these are the internal states. So this chi that depends on the relative coordinates between the projectile and target describes exactly that. Describes the motion, the relative motion between the projectile and the target when the target is in a given state, 0 for the ground state or a particular excited state. So this chi n describes the projectile target relative motion with the target in the excited state n. These chi n's, of course, are unknown. So the purpose of the coupled channels method is to obtain these radial functions, these chi functions. And then you have to remember to obtain the observables remember that we have to go to the asymptotic part of the wave function, of the total wave function. From the asymptotic part, remember we got what Filomena called the S matrix. And from the S matrix, we define the scattering amplitude. And from the scattering amplitude, we go to the cross section. So we go step by step. So remember, yep.
In the previous slide, where is the part of the projectile in the wave?
Well, we could include here actually multiply by an internal wave function of the proton here and here, but since the proton will not get excited in our model, this will not play any role at all. So you could develop all the expressions that we will give here, just keeping also some function here, but you will see at the end that it disappears from the final expressions. So one could, of course, do a more general development of the coupled channels, including both internal degrees of freedom of the projectile and the target. And in some cases, both of them will be important because both of them can get excited. But just to simplify our life, let's think that is why we are thinking on a proton. So this degree of freedom, the excitation of the proton will not be important. And the only internal degrees of freedom that appear explicitly are the target degrees of freedom. Okay? But you are right. One could be more general than that. So let's remind also what is the actual situation that we have in an experiment. We have a source that producing some beam, and this beam is described in our time-independent picture by some plane wave with some incident momentum, Ki. This scatters, this hits by a target, and this produces a set of spherical outgoing waves. And then we place our detector somewhere, and we count the number of particles per second that our detector is receiving. And this is the actual experiment. So remember, the incident projectile is described by a plane wave. Well, if we have the Coulomb interaction, then Filomena told us that we have to be careful because this has to be, at some point, we have to introduce the Coulomb waves. But in all the notation that I'm using here, I'm using plane waves for simplicity. Again, you can imagine how these expressions could be extended to the Coulomb case. Okay? And then the scattered projectile is described at large distances by a set of outgoing spherical waves that behave at these large distances as this. Or in general, by the asymptotic form of this H plus, this Henkel function that may contain this Coulomb phase, and this Coulomb 10 logarithmic 10 in the exponential. That's just to simplify the notation, we will think on this kind of asymptotic behavior. So this is the situation. So in the problem, without degrees of freedom, that is the kind of problem that we have been studying so far. So we have, well, plane wave. So mathematically, this is described. The total wave function corresponds, and this Ki is to remind ourselves that the incoming beam corresponds to a plane wave in the direction Ki. In many of the expressions, if you compare with the slides that Filomena presented the previous days, she chose the incident direction as the Z direction. So this is the vectors that disappear from here. So this will become this R will become the Z direction. But more generally, we could write this in this way. And then a set of scattered waves that at large distances behave like this, behave as a spherical wave multiplied by some function that depends on the angle. And you remember that the square of this function gives us the differential cross section, gives us the distribution of particles according to the angle. And the particular form of this F will, of course, depend on the nature of the interaction between the projectile and target. So without specifying the nature of this target, we cannot say anything else about this F. So F, remember, is the coefficient of the outgoing spherical wave large distances, and the square of f give us the cross-section. Now we introduce the degrees of freedom of the target, as we have done before. So our wave function contains several of these chi's. So remember, we have a superposition of different an expansion on different internal states multiplied by these chi's, and the asymptotic behavior of these chi's will be different if we are in the ground state or if we end up in an excited state. Initially, we are typically in the ground state, so the plane wave is only in this ground state. So our incident momentum, K0, corresponds to the ground state of the system. So we start from the ground state, and one of the possible processes that may happen is the elastic scattering, which we have a spherical wave with the same momentum in modulus, a different direction, but the same modulus of the momentum, K0, K0, multiplied by some f. So this f, 0, 0, so this notation means we start reading from the right to the left. So we start in the ground state 0, and we end up also in the ground state. So this is elastic scattering. But for the inelastic channels, we don't have a plane wave, because initially the system is in the ground state. But of course, after the scattering by the target, some of this spherical wave will correspond to the target in the excited state, in one of the possible excited states. So they may have an outgoing wave, even if they don't have an incident plane wave. So the interaction will produce these scattered waves in the state n. So we have to introduce another f, another amplitude, fn0, and in our notation means we start from the ground state 0, and we end up in an n different from 0, and this corresponds to inelastic scattering. So we have been forced to generalize the concept of scattering amplitude. So now we have a sort of matrix. We start from a given state, and we end up in the same or a different state. But besides that, everything is the same. So, for example, the cross-section, the differential cross-section going for the population of the state n will be this fn0. And remember that this, what Filomena said the first day, that we have to introduce some velocity factors to account properly for the flux. But it is convenient to introduce this f-twiddle that contains already these factors included in the definition. So we avoid to write all the time these velocity factors. So some books work with this f, some other work with this f-twiddle. Any question? No? Is it everything clear? Yeah? Okay. So we have defined a model wave function. We know what is the asymptotic behavior that this function should verify, but we say that we have some unknowns, these chi's, that have to be obtained, and they are obtained by solving this model equation. If we want to write this properly, remember we have some p's and some q's somewhere, so this would be actually a simplified way of writing our Schrödinger equation within the p space. But we are not writing all the time the p psi, so this model wave function would be something like the exact wave function, a known, of course, wave function, multiplied by the p projector, so the projection on some model space. And all the interactions that appear here are to be understood in the same way, as some effective interactions within this p space. Okay, so this is a simplified notation of what yesterday Filomena put in a more general way, in a more formal way. So now the idea, and this is a good exercise for you, is so the idea is to obtain equations for the chi's. So we develop this psi as we shown in a few transparencies. So it's as an expansion in these chi functions multiplied by the internal states, and then we multiply the equation by one. We choose one of the internal states. We multiply this equation on the left by the conjugate of this equation, and we integrate in the internal coordinates, the psi coordinates. So for each of these internal states, we get an equation of this kind. So imagine that we have multiplied by the function, the internal function n. So this is the equation that we get. Everything in the Hamiltonian, so we are integrating in the internal coordinates. The kinetic energy term does not depend on these internal coordinates. So this is a diagonal. This is transparent to this function. But the potential, remember, contains a dependence on these xi coordinates, on these internal coordinates. And in general, we may have diagonal terms that have singled out on the left of the equation, but also it may contain some non-diagonal terms. So in this expansion, we will have terms like this, and this is a simplified notation for this integral. So we will have functions coming from the expansion of the model wave function on the right, multiplied by some function on the left. So in general, we may have a complete matrix of these coupling potentials. So these coupling potentials are the most important part of these equations from the user point of view, because most of you will, many of you or some of you will run coupled channels or DWBA calculation, but you don't have to write your coupled channels code because someone else have done this before for us, so we don't have to write our own code. But so our connection with this code will be through these coupling potentials. So we will have to supply in some way the information corresponding to this. Then the code will solve these equations for us. But this is where the user has to interact with the code through these coupling potentials. So essentially, everything that I will say beyond this point will be related to these coupling potentials in some specific models. So all the structure information or our model information is contained in these functions, internal functions, and of course in this V, the interaction, that depends on our model assumption. So our model assumptions are contained here. So just to summarize what we have seen so far. So optical model that you have seen the previous days, you have a Hamiltonian of this kind. There is no explicit mention to any coordinates. So this V should be understood as some effective interaction. So remember, this is a bare interaction plus some complicated object with some projectors and sort of propagators and something very complicated. But anyway, it is everything in principle contained here. And this V is meant to describe only elastic scattering. So all other processes are included in some implicit way in this V by some microscopic model or some phenomenological fit of the data that you have been doing in the afternoon sessions. Okay? So the internal states are not considered explicitly at all, and our model wave function, it contains just one term. And this term is a solution of the Schrödinger equation that eventually we can develop in partial waves and blah, blah, blah. For the coupled channel, we generalize the Hamiltonian in order to include the internal Hamiltonian of the projectile, the target, or both of them. And the interaction should contain some dependence, not only on the relative coordinate, but also on this internal coordinates of the target or the projectile. Okay? If we want this V to account for the excitation of the target. Yeah? So our internal states will correspond to some eigenstates of some model Hamiltonian, this small h, and the total wave function in the coupled channels method is expanded in this internal states. And we have some unknowns here that in this case will be a solution, again, of this Schrödinger equation that can be written in terms of a set of coupled differential equations. I didn't say it before, but it is obvious that these equations, so we have a set of equations, they cannot be solved one by one because they are coupled. They have the the solution of the n function, chi function, will depend on the rest of the solution. So this is a set of coupled differential equations. Okay, so going from yesterday, you saw also the DWBA approximation, so a way of deriving or going to this coupled channels method to the DWBA approximation is by making a perturbative solution of the coupled equations. So imagine a simple case with only two states that I will label as 0, ground state, and 1. So our model wave function will contain only two terms. This one that describes elastic scattering, this one will describe inelastic scattering. And we think, for example, on this lithium-7 target. So these are the set of coupled equations. So this, remember, the V00 is a simplified notation for integral or ground state interaction. And this V01 is the transition potential, is the potential that tells us how easy it is to go from the ground state to the excited state. So this is the term that couples the solution of the elastic scattering to the inelastic scattering. And we have, of course, the equation for the inelastic scattering that is coupled to the one of the elastic scattering. So we can think, without making strong arguments, but just naively we can think that in these two terms, the elastic scattering in general will be the dominant one. The biggest peak in the spectrum typically will correspond to the elastic scattering. So this component will be dominant with respect to this one, over this one. So as a first approximation, we can think that in this first equation, this second term, that is called the source term of this equation, can be neglected. So we can get a good approximation of the chi0 by just neglecting completely this second term. This is this solution. And then, now this equation is uncoupled. So we can solve it and obtain this chi0, this approximated chi0, and insert this solution into the second equation and get an approximate solution of the chi1. So we don't have to solve anymore a set of coupled equations. This is the first order solution in an iterative procedure. Okay? So this corresponds actually to the DWBA. There is a non-trivial step going from here to the actual expression of the DWBA that you saw yesterday. And this non-trivial step relies on some green function techniques and so on, so we will not give so many details. Just to remember that what we have to do, once we have this, that formally could be written as this term divided by this is a kind of propagator. But, so we have to look asymptotically to the form of this chi1 and look at the coefficient of the outgoing wave. And if we do that properly, as I say, this is a non-trivial step. So if we do this properly, this F10 corresponds to this expression. And yesterday, you, in a different notation, you saw this kind of expressions. So what we have here is the following. So look at one thing that is important, the chi that I have here and here, they contain a twiddle. This is because they are solutions of the homogeneous equations without the source term. So these are the solutions of these the two equations, neglecting the coupling between the two equations. And in between, what we have, V10, is the transition potential between the two channels. So these are a sort of unperturbed solutions of the equations, and this is the transition between them. Okay, so schematically, we imagined we have a system with a couple of states. We can solve this problem to all orders. This is a coupled channel, or we can solve only to first order by solving first the equation for the elastic scattering and then using this solution in the inelastic scattering. So this means that in this approach, in this DWBA approach, the elastic scattering is not affected at all by the solution of the inelastic scattering because we have solved this independently. But we may include in this V00, we might include some, instead of using this transition potential, we can use some phenomenological interaction just fit to reproduce the elastic data, and this is actually what one usually does, to use some effective potential. So the next slide is just a summary of this DWBA. So in practice, one separates the interaction into terms and central interaction and the rest of the interaction. This central interaction does not depend on these internal coordinates. So we, using this V0, one solve the solution, the uncoupled equations for the initial and final channels. I write this I and F because this V0 could be chosen differently for both channels on physical grounds. And in Fresco, you have actually this possibility. Remember that for each pair of excited states, you can define a different potential. This is the C-pot variable, remember? So you can choose a different one for some physical reason. Then the DWBA approximation is obtained this way, where this delta is the transition potential given by this expression. So this is just a summary of what we have seen. This is the DWBA approximation in one slide. Okay, let's complicate a bit more. Still half an hour. I'm exhausted already. And you must be even worse. But, okay, let's go ahead. We have been labeling the states by just one index n. So without entering into what is the nature of this state, we said the ground state of lithium-7 and the excited state, n equals 0, n equals 1. But in practice, we know that this state will be characterized by some angular momentum, the spin. No? So the ground state of lithium-7 is 3½ minus, and then the excited state is 1½ minus. So we have some additional quantum numbers going on. So we have to extend our formalins, or it is convenient to extend these formalins to take into account these properties of these states. And the reason is that the total angular momentum of the system has to be conserved in the process. So it is useful to obtain solutions with good total angular momentum, as in any other problem. When you do structure calculation, you always get solutions with total angular momentum. Also here, you obtain solutions with good total angular momentum because using the property that it must be conserved for the full system. So it is maybe not conserved for the projectile because or the target, because the lithium-7 will change from 3½ minus to 1½ minus. But this means that this angular momentum that is missing there will go to somewhere else. In particular, this can go to the relative motion, to the big L. So again, just to set our notation to make it clear, so let's consider, now I'm switching to projectile. So we have a projectile with internal angular momentum capital I, with some internal degrees of freedom. This is the target, and the L is the orbital angular momentum that corresponds to the relative motion. Of course, we could also include here the spin of the target, and then we will have to take into account for the conservation of the total angular momentum. But again, just in order to simplify our notation, we will consider only the spin of the projectile, and one can imagine a way of extending these formalins. So then if you go to any of the books that we have recommended, then you will find the general solution for that. But the idea is the same, so we will learn essentially the same thing. Okay, so remember that in the one channel case, so in the case without internal degrees of freedom, you obtained the solutions by making some expansion in some Legendre polynomials, characterized by some L. So the idea is to separate the radial part, this chi depending only of the modulus of R, from the angular part. This was the idea of this expansion, and to get some equations for this radial part. So instead of having a three-dimensional differential equation, you end up with a one-dimensional equation for these radial coefficients. So this is the idea of making the expansion of separating the angular part. Remember? Yeah? It's funny because even those that are sleeping say yes. So at least they seem to be listening so far. Okay, so now we have to complicate a bit more the formalism, because we don't have only to separate the radial part, we have to worry not only about the angular variables, so the spherical harmonic, but also about the internal states. So our function, our wave function, depends on the coordinate, on the vector r, but also on the internal coordinates. And we have to separate all this and just to single out the radial part. So we defined what is called a channel basis. So a channel basis is a basis that contains all the internal states plus the angular part. So it's a generalization of these Legendre polynomials or spherical harmonics in the expansion. So this is our channel basis for our problem. It contains spherical harmonic, the internal part, and they are coupled to a total angular momentum J. So the I couples to L to give a total J. And this is coupled through a Clebsch-Gordon coefficient. And this IL could be omitted here, so we can define the basis without this, but it is convenient because if we don't put it here, it will appear in other parts of the wave function that are less convenient. So we put it inside the basis definition. And a short notation for this, remember, is this. So this is a very convenient notation because it tells us that we couple L to the internal angular momentum, I, to give the total J. Okay? So this is probably, I'm spending some time in this because this is probably the most complicated part that I'm going to present. And at least to me, it was something difficult to understand the first time, and also the second time that I listened to it, and the third time. And little by little, you get used to this. But so I imagine that for you, it will be also strange to see the kind of expressions for if this is the first time that you see the. Okay, but the idea is just that we want to make an expansion similar to the expansion that Filomena did, but now our radial coefficients that are defined here for total J are multiplied by these channel functions. And this channel function depends on all these quantum numbers, the total J. This beta is again a short notation for the quantum numbers n that correspond to the excited state, whatever, the L and the I, all these quantum numbers. So this expression with some coefficients you can compare with the expressions in the case without internal degrees of freedom. Okay, but the idea, lost with the notation, is just to isolate the radial parts and to use the fact that the total angular momentum is conserved. So we will have a set of equations for each total J. This is the idea of what we want to do. So for each total J, we will have now a set, a number n, of channels beta. This means that, for example, if I fix the total angular momentum, there will be different combinations of L and I that will couple to this total J and parity, but I'm not putting the parity explicitly, again, for simplicity, but the parity should be also there. There's some pi letter, but we have already enough letters in the notation. Okay? So, yeah.
What's the meaning of MC?
Of M?
MC.
What? Sorry. What is NC?
Yeah, MC.
DC? No.
MC.
MT? This is total angular momentum, sorry. And this is the projection of the total angular momentum, the M quantum number. So I write the T just to distinguish, because for the internal state sometimes I will skip this I. So this is total. This is the projection on the z-axis of the total angular momentum J.
So it's a projection
of J.
Onto what?
On our z-axis, the reference axis. So for each angular momentum, you have the modulus that is related to the j, and the projection on some axis that is the m. So all these m's are projections on our set axis.
So the MJ and T are the same thing.
Ah, okay. Sorry. Now I got it. Yeah, this is a mistake. This should be the same letter. So I tried to change it on many slides. So probably there are some of them in which I forgot to. So the J is the T is the same. I don't know if this was you. So this is a mistake. One of these should be changed. Yes. Yeah.
So we average over projections with the recoupled in the last equation. Is it recoupling or average over projections?
Again?
The last sum over MT.
This?
Is this an average over spin projections? Another spin coupling going on with that?
No, this is the same as this M.
Okay.
It should be the same. It's just that so you have an expansion of these functions, and these functions depend on J. Again, it should be an MT. So they will have three different M's that are the same thing. So it's terrible notation. Sorry. So it's not an average. It's an expansion in some basis that depends on this M. That this should be the same as this M. So now we put this form into the Schrödinger equation to get this the solution of this chi as this radial function. And so these radial functions, again here there are some steps that is good that you use by yourself. Should verify this equation that is very similar to the equation that we have before, but now it's an equation only in one variable, that is the modulus of R. We don't have a vector equation as we had before. So this is what we had gained. Before it was a three-dimensional differential equation coupled to other equations. Now at least it's a one-dimensional equation for only one variable, R. So this is what we had gained going from the general wave function to to solutions with total angular momentum. And again, we can define now some coupling potentials in this channel basis. So now these coupling potentials are defined as the matrix element of, again, the V interaction between different states, internal states of the channel basis. And since the channel basis depends on these angular variables R and the xi functions, then we have to integrate on both variables. And these coupling potentials will depend on the beta prime, so the initial and final channels, and also on the total J. Okay, so we have defined some general coupling potentials at the beginning, but now we are defining these coupling potentials in this channel basis that are obviously related to each other. Okay, but this is only the beginning of the story. Now let's complicate a bit further the situation. So we have for each total J, so remember this equation depends on total J, but for each total J we have n coupled differential equations, because beta, we have n possible values of beta. So for this total J we have n possible, n independent solutions of this equation. So this equation contains, each of these equations, n independent solutions. So we have n coupled differential equations because I can change, I go back here, this beta can have different values. So for each of these beta have one equation. So for each total J I have n possible different equations. And remember, n is the number of values of beta compatible with this total J. So this means that we will have n possible solutions, n independent solutions to this set of n equations. So the standard choice, the common choice, is to build solutions characterized, there are other ways, but the standard choice is to build our solutions characterized by a given entrance channels beta. So we choose one of the betas that I identify as beta I, and I call this my entrance, my initial channel. So I characterize now my solution not only by total J, but also by one beta of my choice. I make a choice of beta, and this is one of the solutions. And how many solutions do I have of this kind for each J? I have n possible solutions, one for each beta. So now the expansion is generalized as follows. So we have this expansion in terms of this channel basis, but the radial functions now contain two indices, two labels, contain the dependence on beta, that is, we have a sum in beta, but contains also a dependence on the channel that we have chosen as initial channel. So the interpretation of this is that the total angular momentum is conserved. So we start with total J, we end up with total J. So the interaction can change L or I, but not the total J. It is conserved. But the beta can change. So if we start with some particular channel, beta I, the interaction can change this beta, and the system can end up in a different channel. So in principle, in all possible final channels. This is the interpretation of these chi functions. So these chi functions must be, as in the single channel, must be regular at the origin, and asymptotically these equations are solved with the following conditions. So asymptotically, they must be a combination of the solutions of the free equation without interaction. And these solutions, remember, are the h minus h plus, these Hankel functions, or the f and g, the regular and irregular functions, or some combination of them. So for example, if we write the boundary condition in this form, which was to make this kind of combination, then the coefficient of the h plus function corresponds to the S matrix. Now, remember, we have so our boundary condition is that we start with some beta I. This is our initial channel, but we can end up with a different beta. So now the S matrix is actually a matrix. So now it's properly a matrix, because for total J we have all possible combinations of beta I and beta. So this S matrix, now the name makes more sense as compared to the single channel case. So we have to solve the equations imposing this condition, and by imposing this condition, the code, Fresco for example, will extract for us this S matrix for each total J. So for total J, it will give us a matrix of complex numbers. Or we can write it in this way, as a combination of the regular solution time plus the outgoing Hankel function h plus multiplied by this T, and this T is the T matrix. So they are related in this way. This is a generalization of what you saw in the one channel case. So these expressions are just a generalization of the expressions that you saw in the one channel case. Okay. Again, let's go further. So the general solution, we are obtaining solutions characterized by a total J, but in our experiment, our beam is not characterized by total angular momentum J. It's characterized by some momentum vector Ki. Remember, we have a plane wave, for example, and a set of scatter waves. Actually, we have to include, remember now, the initial state of the system. So it's characterized by a plane wave multiplied by the internal state of projectile or target, the one that we are considering explicitly, in some specific state. So remember, this I corresponds to the internal state of the nucleus being excited in some initial state and with some projection. So this is our physical initial state. And then we have a set of scattered waves that, again, we keep here this index just to remember what was the initial condition, but then this scattered wave will contain components in all possible excited states of our model. So this solution can be constructed once we have obtained the solutions characterized by total J. This is what we have obtained by solving coupling equations, solutions characterized by total J. We can make an appropriate linear combination of these solutions. So these are the solutions that we obtained from the coupled channels, characterized, remember, by an incident beta I, total angular momentum J, and projection MT. So these are the solutions of our coupled differential equations, the psi plus. So we make a linear superposition of these solutions with these coefficients. In order we can construct our physical wave function. So this psi plus, remember, we wrote this as a sum of the possible final channels beta with some radial coefficients. So these coefficients can be obtained imposing the condition that this function contains a plane wave plus something else. So extracting from here the contribution from the plane wave. So you actually did that in one of the homeworks for the single channel case. And here you have many more quantum numbers, but the idea is the same. So I propose you as an exercise trying to obtain the expression for these C coefficients, that is comparing this. You have to extract in this expression the contribution of a plane wave. So this means to make the partial wave expansion of the plane wave here. It's a bit more involved because you have also this contribution here, but well, the final result is not very complicated. It's this one. Okay? Still 15 minutes. Then, finally, so remember that our final goal is to obtain the scattering amplitude, because from this scattering amplitude we get the cross-section. So in terms of these coefficients, of these S matrix coefficients, the expression of the F, that is, again, this is not a trivial step, so you require some step, but I'm going to the final result. So the F, by looking at the asymptotic behavior of this part, so the idea is from this expression we isolate, we single out the plane wave, so the remaining part should be the scattered wave. So we look at the scattered wave and we see how it behaves asymptotically, and then we realize that asymptotically it's something multiplying some spherical wave. So the coefficient of this gives this expression. So this is another exercise, gives this expression that contains the S matrix here, the multi-channel S matrix. So what Fresco actually does is to calculate the radial equations for a total angular momentum. So for each total angular momentum, the code will do a separate calculation, obtain the S matrix. So it's a matrix with n times n for all possible channels, and then construct this scattering amplitude for all possible final states of the projectile of the target using this kind of sums. This is how the code works internally. So any coupled channel code will do something like that, going from S matrix to the scattering amplitude to generate this F. Sometimes we write the F as a function of theta, of the scattering angle, but I write it in terms of this K, just to remember that this angle is just the angle between the initial momentum, Ki, and the final momentum, K. So you have the initial and the final momenta here. Okay, and then finally the cross-section is related to the square of this amplitude. This amplitude will depends actually on the projection, of the spin of the projectile, of the target, So you see there is a projection here, and this is something actually that can be measured. So this is an observable. So in principle, our beam could be aligned experimentally to give some given projection. Statistically speaking, to some extent, we can have 90% of polarization, that is called, in some direction. So this is something that we can actually obtain experimentally. And the same thing, in the final situation, we can measure, in principle, ideally, also the projection of the spin of the projectile or the target in some, with respect to some axis. So this is something that we can measure. But in practice, many experiments don't measure that. So what we actually measure is a sum over all possible final projections. So we measure the final product irrespective of the projection, and an average over the initial possible orientations of the spin. So this is what this sum and this coefficient means. This is a sum over all possible final states. We are not interested. We are summing all possible final states, and we take a statistical average, assuming that it is randomly distributed, the projection of the spin, over the initial projections. Okay? Okay. It looks like time is going backwards because so you have any question before I continue? Are you completely lost at this time, or? I guess that it's difficult to get all the details of the formulas, but the idea, at least, yeah.
I don't understand what is the link between key and key beta G and key beta E.
So this chi?
Yes, and the previous this?
This?
And with the previous at the beginning.
Okay, at the beginning, yeah, our chi's depend on the vector r. So here we haven't done any angular momentum expansion. So now what we are doing is taking advantage of the fact that the total angular momentum is conserved. So this chi now can be understood as the radial part of these previous chi's related to the radial part.
But the previous chi is also
these chi's.
radial part. No?
It's also
Radial part.
no, this contains both angular and radial part. Okay. Implicitly, because that is why we have a vector here. So if we expand this, we will get some radial part, that is the other chi's, and some angular part. But so we are expanding actually in states of total angular momentum. So we are coupling also to the spin of the projectile in this case. So these chi's are not exactly the radial part of the other chi, because it contains also information on the internal state of the projectile. So are some radial functions, radial coefficients of the expansion of the total wave function. So at the beginning we started with an expansion with some chi depending on some vector multiplied by some internal state. This was our first approach to the problem. But now we decided to make a new expansion that is equivalent to the previous one, in which we emphasize the fact that the total angular momentum must be conserved. So we expand in terms of a basis state characterized by a given total angular momentum. And this is why we have this chi here, which are these radial coefficients in this basis. Okay? So the previous part is a schematic way of presenting the coupled channels method, but in practice, how it is done is in this way, by making this kind of expansion, because the other way, our equations are vector equations, so are three-dimensional equations that are coupled to other differential equations in 3 dimensions, so it's much more complicated. But here, our equations are one-dimensional equations, only these are modulus. But, well, vale. So this is the meaning. So let's go a step further before, let me see how much we have here. Okay, so I think that we can finish the formal part and then go to the specific models in the second part. So now we have, remember, we have this, let me go back a second. We have these coupling potentials that are the matrix elements of our interaction potential between states that are characterized by a total J. So in practice, it is also useful, instead of putting here a general potential, to make also some expansion, some multiple expansion of this potential. And the reason is that because we have states here with total angular momentum, in this expansion, only some of these terms will contribute. So just as an example, you have, for example, oxygen 16, 0 plus ground state, and you are going to study excitation to the 3 minus excited state. So you know that the interaction potential, the only contribution comes, if you make a multiple expansion of this potential, the only contribution will come, in this case, from the octuple term of this interaction potential. So if you make an expansion, dipole, quadruple, octuple, blah, 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 only the octuple part will contribute. So this is a useful way of selecting the part of the interaction that is relevant for a specific transition. So we have to develop a bit further these equations in order to emphasize this conservation of angular momentum. So we will make an expansion of these V's. Okay, so we want to solve this with this coupling potential, but we will develop this V. We will make a multiple expansion of this V, this projectile target interaction in multiples. So this is the last part of this presentation. So in general, the V is can be expanded in this way by separating in these spherical harmonics. So this depends on vector R, but we can make an expansion in these spherical harmonics separating the angular part. So we will have something that depends on the R modulus, but also the dependence on the structure will be still there, must be still there. It cannot be here, the spherical harmonic, so it should be here. So the coupling potential, if we have states characterized by some angular momentum of the projectile, initial and final, and we put this expansion inside this matrix element, this coupling potential will contain terms of this kind. This square of 4 pi is introduced many times for convenience. So for lambda equals 0, we have the spherical harmonic is 1 over square root of 4 pi. This will cancel out. For lambda equals 0, this will correspond just to the central potential. For Coulomb interaction, this will be just the product of the charges, times E squared divided by the modulus R. So we don't have additional factors. That is the reason of putting this explicitly. But in some other books, they don't put it here. This means that this will be included inside this V. Okay. In many cases, one can go a step further, and these V coefficients that depend on both modulus R and the internal coordinates can be separated, factorized in terms of one factor that we will call the form factor, F times some tensor, some object here, depending on the internal coordinates. So this is not a general case, but many times this will happen. And it will be useful because when we calculate the coupling potentials, we will get a nice factorization of this kind. So we put this into this expansion. And so we have all the structure part here. We have now the radial part, the structural part, and the angular part, everything factorized. So that when we calculate the coupling potentials, we do the same thing here. And since these states they depend only on the internal degrees of freedom, then they will not affect this radial part. So this radial part will come out, and we will have to calculate only these matrix elements of these objects, of these T's. And we will specify now the form of these T's for specific models. Okay, so this is a more general case, but this is a not so general but very common case. Okay? We can say something else, something more. We can expand a bit more. So this matrix element, so these are these V's and this T, this has the same rotational properties as this Y. This is because the V, the full V, is a scalar. Maybe this means nothing to you, but you believe me that this V has the same properties as the spherical harmonics. For example, these transformation properties. So this means that we can apply the Wigner-Eckart theorem that you have studied. All of you have studied Wigner-Eckart theorem at some point. Yes? Does anyone? Is anyone here that never? You never heard about Wigner-Eckart? Okay. Oh, this is in just in 2 words. So the Wigner-Eckart tell us that if we have a matrix element of this object, this tensor object, this could be a spherical harmonic, but in general could be something more general with the same transformation properties. So this can be written as a product of a Clebsch-Gordan multiplied by something that does not depend on the projection. So all the dependence of the projections, Ni and F, is actually given by this analytical coefficient. So we can calculate it separately. It's proportional to this one. So this C is something that does not depend on the projection, and this is something that does not depend on the projection. We have several possible choices, because depending on what is my choice of this C, then this thing will be also different. This is called, with double bar, is a reduced matrix element. Reduced matrix element. And this is something that, I repeat, does not depend on the projection. Depends only on lambda and on the total angular momentum, initial and final, but does not depend on the projections. Okay? So there are, in nuclear physics, there are many choices, many possible, infinite number of choices, but there are 2 popular choices that are also a source of confusion, because when we mix information from different sources, sometimes they use different conventions for that, but it's good to have in mind what is the convention used by the authors, and to see if this convention is the same one that we are assuming. So 2 popular conventions. I gave just some number of some names of popular books that use these conventions, but other people call it in a different way for sure. So the Bohr-Mottelson convention is to take this C as this factor, and so the Wigner-Eckart theorem adopts this form. So this Bn here tells us that this reduced matrix element corresponds to the definition of this of Bohr-Mottelson. Another popular definition is the one used, for example, in Sacher or Bing and Sacher book. That is to take this C as this factor that in our case, since lambda will be integer, this factor is actually 1 in our case. So the Wigner-Eckart theorem will adopt this other form. So the reduced matrix element, of course, the full matrix element has to be the same. This is the physical thing that we calculate. But the reduced matrix element will be different. And since we normally work directly with these reduced matrix elements, because the Clebsch-Gordan coefficient can be put later on, or it's put by the code, inside the code, so we will provide typically the codes with these quantities. So the relation between them is that the advantage of the Bohr-Mottelson convention is one here. So the reason why they put this factor is that this reduced matrix element is symmetrical when you interchange the values of the angular momentum initial and final. So this is something convenient, because this means that, for example, you only have to give the information for a given transition 1 to 2, because the 2 to 1 will have the same reduced matrix element. So this is why some codes prefer this choice, and Fresco is one of these codes. Okay, so using this Wigner-Eckart theorem, and going back to our transition potentials, so we can now split the matrix element of the potential into this using Bohr-Mottelson. Sorry, I didn't say using Bohr-Mottelson convention. We have this Clebsch-Gordan coefficient with this factor times this reduced matrix element. Or if we can separate, we saw before, the radial part from the structure part, then we will have the reduced matrix element of this T object times the radial part. So this will become, this in red, will become this. So all the structure information, and this is probably the main point that I want to make here, is that all the structure information or our model is contained into these reduced matrix elements of the interaction potentials. So this is the information that a coupled channels code or any code requires to make a calculation, the information for us. From the user point of view, are these reduced matrix elements. So in the general case, we have something like this, and it will depend on the lambda and the initial and final angular momentum. And if we can separate the radial part, then it will be given by this form. So in this case, for example, we have to supply the code with two elements, the radial form factor, this is called form factor, and the reduced matrix element for a given transition. So this is the information that the code requires. Once the code has this, it can construct this matrix element, it can solve the couple equations, and so on. So you see that at some point you can almost forget everything that I have said in the last hour and just remember this line here. So this is the minimal information that you need to remember for your calculations. Okay?
The summation with regard to mu should be probably ahead of the Clebsch-Gordan coefficient, which contains mu in the second.
In the second one, yes, it should be put, yes, it's a mistake, you are right. This sum should be put before the Clebsch-Gordan, of course. But anyway, in this case, this mu, actually I could omit this sum. Why? This sum here could be omitted here. Why? I could just remove this sum here. Can anyone tell me why? Yeah.
The projections must sum up to the total projection.
Yes, because of the Clebsch-Gordan, this mu is just the difference between the MF and MI. So only one value of mu survives from this matrix element. So actually you can simplify this, removing this mu in both expressions. Okay? Because it's determined by MI and MF. Because of the properties of the Clebsch-Gordan coefficients. Good. And I think that this is a good moment to stop and to have a rest and think about this.